Welcome to the next lecture on casting. In this lecture, we will try to see various processes of casting. So, casting can be classified into two: expendable casting and non-expendable casting. Expendable mold casting are molds which are broken once you take a component done out of it or a part or done out of it. Non-expendable mold casting is where it is used for mass production. You can try to make a mold out of steel or metal and then you can keep using it multiple times. When we talk about expendable, there are permanent pattern casting. The pattern can be made permanent. That means to say it can be wood, it can be iron, it can be ceramic pattern. And then you can use this for sand casting, plaster mold casting. Plaster mold casting, where have you seen? Plaster molds are used for when you have a broken arm. So, you will always put a plaster of Paris and the plaster of Paris will try to take the shape of your arm. Plaster mold casting are used for making a very fine feature output. For example, you can make ceramic dolls out of plaster mold casting. Then when we go into expendable, this is temporary pattern casting. In temporary pattern casting, the pattern will melt and get vaporized. So, you have evaporative casting and you have investment casting. When we talk about non-expendable mold casting, you have die casting, centrifugal casting, pressure casting and many more. There are many more, but keeping time as a limitation, and if you understand these things, you can extrapolate the knowledge for new casting process. So, now let us look into expendable molding and permanent molding. What is expendable molding? Expendable molding means where it is made out of sand, it is broken once the part is taken. So, here we have shell mold. What is shell mold? We have a pattern, right? This is a pattern. We heat the pattern. We put it on the top, we heat the pattern. In the box, dump box, what we do is we fill it up with sand and resin. Now, what do? We have a handle here and then we rotate. Moment you rotate, the sand with the resin binder gets on top of the heated pattern. Now, when you rotate it back, the free sand with the resin will fall out and there will be a thin skin of pattern which is generated. So, you see a thin shell which is generated. Now, what do? You take the shell and bake it in a furnace, given temperature whatever it is. Now, what you get? You get a hardened shell. You remove the shell, you get a hardened shell. Now, using that shell in sand, you can try to make a mold, right. So, that is called as shell molding. So, now let us go through the text which is attached. Shell molding uses 9 millimeter thickness sand shell with thermosetting resin. A heated metal pattern, precise molds with sand and resin are made. The dump box is inverted to allow the sand and the resin mixture to fall on the metal pattern or the hot pattern to form a partial shell. The box is repositioned to remove all the loose particles and the sand shell is heated in an oven for complete curing. Patterns and two halves of the shell molds are assembled, supported by sand or metal shot in a box and pouring is complete. The examples of the parts made using shell molding includes gears, valve bodies, bushing and camshafts. So, these are some of the examples of shell molding. So, here the advantage, it provides high precision and fine details, achieves high precision with minimal machining, very precise. It is, we will say it as near net shaping method. So, machining is also not required, only small finishing is required for assembly. It reduces post casting defects and rework. It is expensive metal patterns are there, not suitable for small quantities. For large quantities, yes, this can be used of. Next is vacuum casting. In vacuum casting, what we do? We try to keep a sheet, right? A sheet, plastic sheet. Then we keep the pattern on top of a box or surface, a pattern. Now, what do? Is we try to draw a negative vacuum, or we try to suck from the one side of the box. Now, the plastic sheet gets wrapped over the pattern. So, there are vent holes through which the vacuum is created. So, the plastic sheet, it can be little heated. So, it is soft. So, it can just go and wrap. So, this is almost like when you buy a mouse, you can see a plastic sheet on just on top of your mouse, right. So, it is almost like that. So, a plastic sheet, a pattern, a mouse is kept, and then you vacuum suck it. So, it tries to take the profile. In the next one, what you do is, moment the pattern is made, so then what do? Is we try to have a pouring cup, and then we try to fill it up with sand. Next, what we do is, we try to put a second plastic sheet on the top, and then we try to again suck through this, right. These are all vacuum drawn. So, we suck through this. So, now what happens? The top surface is also formed on top of it. So, now what is happening? You will try to remove. So, here you will have a plastic film on top, then you will have a plastic film on the bottom. Now, with this, what do? Is you try to pour the liquid metal, and you try to get the shape, or you try to get the mold. From the mold, you try to get the part. So, now this is vacuum casting. This is precisely used for high precision feature items, and it also can be used for batch production. In this process, a sand mold is held together by vacuum pressure and not by chemical binder. Why? Because here what they want to do is, they want to reuse the sand. The term vacuum is in the process refers to making the mold rather than casting operation. The casting operation is as same as the other processes. No binder is used, so the sand can be recovered. Mechanical ramming is not required. Absence of moisture prevents defects in the product. Molds are expensive, not suitable for materials with very high melting point, because they will burn the plastic, and they are not suitable for large casting because of size constraint. Why? You have to have a large vacuum sucking pumps. Next, let us see the investment casting process. In investment casting process, what we do is, we try to have wax patterns. This is the top view, this is the side view. So, now such wax patterns are attached to a wax sprue. This is the sprue, pouring basin sprue. Now, at regular intervals, I attach the wax pattern. Now, what do? Is I try to have this wax pattern immersed inside a slurry. This slurry is ceramic plus water. You have slurry, and this slurry, what do? Is we try to immerse the pattern with the inside the slurry and extract it out and dry the slurry which is sticking on to the part. Now, what do? We have got the wax pattern, and on top of the wax pattern we have the slurry. Now, when I try to pour the hot liquid into it, the wax pattern melts and vaporizes, and the rest of the portion where the mold is available, the part is made. So, if you look at it, you will understand there is a long sprue, there are runners which are attached, and these are the parts. This is a wax gating system, and these are wax patterns. Now, they are pressed inside the slurry, and you see the slurry shape is there. Now, what do? They try to melt, heat it, and then they try to melt the wax out. So, wax is removed. Now, you have a mold ready. On the mold, they pour the ladle of molten metal. you get the parts made out of it. It is the best method for making intricate parts, small parts, multiple parts in one stroke. Okay. So, before pouring this, the slurry, the heat it and the wax is removed, then the mold is ready. The investment casting, a wax pattern is coated with a refractory material and the wax is melted away during the pouring. Investment refers to completely covering the wax pattern with refractory materials. It is a precision casting process. Using this, we can make casting of high accuracy with intricate details. The wax patterns are created and attached to sprue to form a pattern tree. So, this is a pattern tree. To form a pattern tree which is coated with refractory material to form a rigid mold. The mold is heated to melt the wax, preheating to remove the contaminants and then filled with molten metal to form the casting. Complex and intricate parts can be made. Tolerances of 0.075 millimeter are possible. Good surface finish is possible. Additional machining is not required. So, we get the near net shape done. What are the disadvantages? Longer production cycle due to multiple steps, because you make one pattern, then you make multiple patterns, then you attach these multiple patterns to a sprue, then you try to mix it in a slurry, then the slurry is made a shape and then you heat the slurry, the wax is poured out and then you get a mold. So, multiple steps are involved. Not suitable for large component due to mold size limitation. Expensive tooling and patterns make it less cost effective for low volume production. Stainless steel, high temperature alloy can be cast machined part, blades, components of turbine engines, jewelry, dental fixtures are made by it. Please make a note, friends, dental fixtures and jewelry, goldsmith and dental fixtures crowns are made out of investment casting. Low pressure casting. Low pressure casting is, what we do is, we try to have in a ladle means a container, in a container liquid metal. Now, what do? I pressurize the liquid metal. When I pressurize the liquid metal, there is a orifice or there is a tube. So, through this tube, because of the pressure, there is a tube, the liquid flows through the tube and then comes through to the casting. And now, what you have is, we have a cast part. So, here we pressurize it from the outside atmosphere. So, the low pressure casting, the liquid metal is forced into the cavity, under a low pressure approximately 0.1 MPa from beneath to the surface, so that you get a metal flow upward. Okay. Once the part is made, it is retracted. Advantages: mold metal is not exposed to air, gas porosity and oxidation defects are minimized. The other one is vacuum casting. In vacuum casting, what we do is the variation of low pressure casting, but in this the vacuum is used to draw the molten metal into the mold cavity. So, what do? Is we have a lower die, this is a lower die. So, here we try to have vacuum which is sucking. So, because of the sucking, the molten metal enters and fills the mold, right, and then from the mold you will have three outputs. So, these are vacuums which are done. This is the casting. So, retractable upper die, lower die, and this is a liquid metal. This is a liquid metal which is there. Okay. So, if you look into it, this is vacuum die casting. So, you have a toggle bar mechanism, opening and closing. So, this will be moved back and forth, right. Here you have a die and then you have a casting. So, application: automobile, turbine blade, valve bodies, defense parts and industrial components are there. Die casting, it is the most advanced process and it is the latest process, wherein which we are now trying to make all metal parts by die casting. So, the mass production rate is very high. So, the process involves a high pressure, approximately 7 MPa to 350 MPa, which is used to pressurize the molten metal into the die. The pressure is maintained during solidification. The hot chamber die casting and cold chamber die casting are two different things. In hot chamber die casting, the liquid is, the molten metal is there. So, then what you do is you use a plunger to pressurize the liquid. So, the liquid flows through the sprue or through the nozzle, and then it gets injected into the mold. So, once you have this is one half of the mold, this is the other half. Once the solidification happens, then we use ejector pin to move the die back. It ejects and the component falls down. So, this is movable die half, this is the fixed die half. Okay. Hot chamber die casting, cold chamber die casting. This is hot chamber die casting. In cold chamber die casting, what we do is we try to pour the liquid into a ladle and then we pressurize it. So, this is a molten metal. You have short chamber here, you pour it and then it is pushed and then you get the component out. So, in hot chamber die casting, the molten metal is melt in a container attached to a machine and a piston is pushed to the pressurized metal under high pressure into the die. The pressures vary from 7 to 35 MPa. The production rate of 500 parts per hour is very common. The injection system is submerged into the molten metal and hence possess problems of chemical attack on the machining components. It is suitable for zinc, tin, lead and Mg. This is the hot chamber die casting, plunger, pushed, pot and then you try to get the part. These are all the steps which are involved in the hot die casting. So, faster production with high precision in complex shapes, ideal for high volume production with low melting point metals, better surface finish and lower initial total cost, initial tool cost. So, these are the advantages. What are the disadvantages? The disadvantages of hot chamber die casting is limits to low melting point metal, die wear out due to high temperature and not suitable for large casting. So, these are all the problems. So, you can see here electrical connectors, hardwares, consumer products, medical instruments, small mechanical parts, all of them are made by hot chamber die casting. Hot chamber die casting, the pot is there, liquid metal is there, plunger pushes it, the liquid metal goes through the gooseneck and enters into the nozzle and then it gets into the die. Cold chamber die casting, the molten metal is poured into the mold cavity and the injected under high pressure using a piston. The process involves injection molten metal into the mold such that you try to get the part out. So, the metal is poured into the cold chamber and the hydraulic plunger forces it into the die cavity, ideal for high melting point metals. It produces a high strength, durable parts with fine details, but has a lower cycle time than the hot chamber die casting. Ideal for high melting points, longer die life and produce strong and durable smooth finish parts. The disadvantages are production cycle time is slower than the hot, higher tooling cost and efficiency for high volume small parts. Centrifugal casting is another interesting process wherein which you are trying to produce cylindrical tubes or barrels, right. So, here what we do is the mold we pour from the ladle, we pour the molten metal into a pouring tub. From the pouring tub, it is poured into the metal mold. Now, what do we do is we rotate the metal mold. So, when we rotate the metal mold, because of centrifugal action, a thin wall is formed of metal, thin wall tube is formed and it gets solidified. So, the mold is rapidly rotated and the centrifugal force acts on the metal, causing impurities to segregate towards the center. So, what we are trying to say is, if you have a cylindrical barrel like thing, so here you will have all the segregated items located here, and this we can try to machine and then remove it. So, if you look at the cross section, it will look like this. So, the metal mold is this, centrifugal cast tube which is getting formed is this. The roller is rotated on a two casting machining rollers. So, you will rotate the rollers, these rollers can free rotate, and then this mold is rotated. Used for producing long hollow axisymmetry components like pipes, tubes and hollow bushes without the need of any core. All the sewage pipes are made out of this. There are three types of centrifugal casting: true centrifugal casting, semi-centrifugal casting and centrifuging. Centrifugal casting used for making a pattern in investment casting, centrifugal casting. True centrifugal casting is used for making jet engines compression cases. Semi-centrifugal casting used for making a wheel, pulley, spoke to wheel and alloyed wheels. So, if we look into the application, cast iron water supply sewage pipes are made out of true centrifugal casting. So, in semi-centrifugal casting is used for making wheels, rings, rims, pulleys, flyweights, etc. Centrifuging is used for producing irregular and non-symmetrical valve bodies, plugs, valve bonnets, pillow blocks and yokes, etc. So, in centrifugal casting is also called as roto casting or centrifugal casting technique, CCT. So, what we do is, we have a ladle, we pour it, there is a runner and then the mold is filled. When it is rotated, this is a gate, when it is rotated it will try to form. So, this is true centrifugal casting. The liquid metal is poured, it is rotated, so you get a centrifugal. So, in semi-centrifugal casting you have a core. So, you have a core and the liquid is filled in here and then it is rotated. This is for semi-centrifugal casting. Semi-centrifugal casting, you see examples of wheels, rings, rollers, shaves, pulleys, flies, gear blanks, etc. So, true centrifugal casting, we have seen it in detail. So, the centrifugal casting shapes the casting, making the inner surface perfectly round, while the outer surface are non-round. So, examples we have browsed through it. So, we do not have to repeat it, this is for your study purpose. So, in semi-fugal casting involves partially rotating the mold with slower speeds as compared to that of centrifugal casting, creates a denser outer layer and a less solid inner core due to moderate centrifugal force. Dense outer layer, it forms a dense outer layer. So, here you will have a dense outer layer, right, and a less solid inner core due to moderate centrifugal forces. So, the table is rotated, you get injected. So, these are some of the examples we have gone through in details. So, I do not want to read it once again. So, centrifuging casting. Centrifuging is a casting process where rotating mold shapes molten metal using centrifugal force to create dense and high quality. So, you pour it, you rotate the mold. So, these are runner, these are gates, and then you will see something running and then you will get it. So, these are some of the parts which are produced by centrifuging. So, here are the comparative tables. So, I have put varying processes and I have put the type of casting. So, die casting, investment casting, sand casting and permanent mold casting. The process here, the injection of molten metal into the mold is die. Investment casting is wax model covered with ceramic shell. In sand casting is create a mold with sand, and permanent mold casting is employing reusable metal mold. The advantage, die casting high precision, intricate design, fast production rates. Investment casting excellent details, intricate components and versatile. Then Versatile, suitable for large parts, cost effective is sand casting, and good precision, balanced cost and precision, versatile is permanent mold casting. What are the limitations of die casting? It is limited to non-ferrous alloys. Higher investment for tooling cost, die casting. When we look at investment casting, it is slower production rate compared to that of other casting techniques. Sand, low precision as compared to die, and rough surface finish is there in sand casting. In permanent mold casting, limited to non-ferrous alloys, tooling cost, less intricate details. So, this is permanent mold casting. When we look into cost effectiveness, moderate to high cost, effective for mass production, cost effectiveness. Investment casting, moderate to high costing, suitable for complex shapes. Sand casting is generally cost effective and ideal for large parts. Then permanent mold casting is the moderate cost, balanced precision and efficiency. So, this permanent mold casting is very good. So, primary range of alloys, non-ferrous alloys, aluminium, zinc, magnesium can be done by die casting. Broad range of ferrous and non-ferrous can be done by investment casting. Sand casting we use for ferrous and non-ferrous alloys. Permanent mold casting, commonly non-ferrous alloys and aluminium and copper. So, the applications generally you see automobile components, electronics and consumer goods for die casting. Investments casting, artifacts, jewelry, aerospace components where precision is required. Sand casting are various industries, especially for large and complex parts. Then permanent mold casting is the automotive parts, aerospace components and industrial applications. When we try to compare with the other things, shell molding, centrifugal casting and continuous casting. Shell molding is utilized effective molding methods. The effectiveness of medium to high production can be done. Limited precision dependent on the methods used. Cost effectiveness, it is cost effective for medium to high. It is adaptable for various range of alloys. Application is this. Centrifugal casting, using centrifugal force, you try to rotate and get the shape. It is predominantly cylindrical, limited for cylindrical components only, that is the limitation. Moderate to cost effectiveness can be there. Range of alloys, it can go for ferrous to other things. Application, cylindrical parts only it can be made. Friends, I have not covered continuous casting, but I will try to compare here and I will share you the reading material. Continuous casting, here the continuous flow of molten metal is there, effective for continuous length and consistent quality, limited to continuous shapes. Efficiency depends on the application and continuous process, commonly for ferrous and non-ferrous alloys. Metal sheets and rods are used here. So, when we try to have some of the common defects due to sand, there can be gas defects, there can be expansion defects, there can be adhering sand defects, there can be weak sand defects. In the gas defects, blow holes and pin holes are prominent. Pin holes are small holes which are there on the surface, right. Expansion defects are rat tail, buckles and then scraps are there. So, these are all projections which are just created on top of this thing. Adhering sand defects, rough sand, sand tickling, metal penetration, burn off and burn in. These are all part of adhering sand defects. Weak sand defects are tearing up, stick, sand drop, sand crush, erosion, run out and sand inclusion. These are all some of the sand defects which are possible. So, when we look at the possible casting defects, a cast is there is not proper filling and a void is created here. This defect is called as hot tear. Sand blow is when the liquid is there is a gas trap there. So, this is called as the sand blow. Pinholes are always seen on the surface of the product. Sand wash, when the liquid is flown, there is a turbulence created, the mold material is removed, that is called as sand wash. Scabs are formed on top of the surface of the sand. So, these are all cold shuts. So, cold shut is when there is a liquid flowing from one direction and the liquid flowing from the other direction, they do not meet, before that they solidified, it is called as cold shut. So, you move from here, and you have a improper filling, that is called as cold shut. So, you can have misruns. So, when it is trying to flow throughout the mold, it is trying to the end, there is a air trap which is there, this is called as misrun. So, this is cold shut, which I have already explained. These are cold shots which are there on the surface. This is the shrinkage cavity, and this or microporosity which comes from the air getting released from the sand. These are all penetration defect from the sand casting. The liquid penetrates inside and then it solidifies. The cope and drag, when the mold is there, if they are not properly pinned or tightened, there is a shift which happens between the cope and drag. So, you have a offset, and then a core which is there, because of buoyancy it gets upward, the core gets shifted upward, and these are micro cracks. These are penetrations, these are one single crack which is there from the part which is made, and here is the sand. So, these are called as mold cracks. So, these are all some of the defects, and these defects have to be avoided, and almost all the defects are more focused towards sand casting. So, when we look into the type of defects, I have just written down sand blow, the balloon shaped gas cavity near the surface. So, the gas is trapped during pouring, or it can be excess moisture, improve mold venting and dry sand properties. Pinhole, all the small holes due to trapped gases, it goes to the top and then it is formed in the part. So, gas trapped in the metal, low pouring temperature. Here it improves mold venting and it increases pouring temperature. So, sand wash, these are erosions of mold surface by molten metal. So, here they are metal erodes the sand, and then you have high pouring speeds, they are also there. Improves sand compaction, you will not have the sand washing. Pouring, so it is problem during the metal pouring, improper pouring rates and improper gating system. Remedies are optimize the pouring temperature and improve the gating design. Scrab, which is there on top of a surface, scab is metal sticks to the mold, and high mold temperature. Apply mold coating and lower temperature. Penetration, these are metal penetrates into the surface. So, metal penetrates into the mold and low mold compaction. The mold compaction have to be strengthened. Microporosity, small voids within the casting, the gas bubble traps in the metal, and rapid solidification also leads to microporosity. Mold shift, misalignment of the mold halves. So, properly pin it and vibrations and other things have to be removed. Core shift, if the core print is not properly holding and if there is a buoyant force which acts, which tries to shift. So, movement of the core during pouring, the core movement during pouring can be done. So, here you better reinforce the core structure or you secure the core better. Micro cracks, these are cracks on the mold due to stresses, rapid temperature change, weaken the mold material. So, you have to have stronger molds. Misruns, incomplete casting due to early solidification. So, you have to improve your gating system and also solidification rate. So, cold shut, incomplete fusion of metal stream, interruption flow during the pouring and low pouring temperature will lead to cold shuts. Ensure uninterrupted pouring and increase the pouring temperature. Cold shot is small solidified metal particles in casting. Cold shut, the metal solidifies before the fill and slow pouring causes this solidification. Cold shut, let us look at the figure. Cold shots. Shrinkage cavity, a hollow cavity due to contraction. Shrinkage cavity is you see on the top, right. The metal contraction too much during cooling. Inadequate feeding also leads to solidification. Sand burnout, it is metal adhering to the mold surface. Metal sticks to the high temperature, excessive oxidation. So, it leads for mold coating and pouring low temperature. So, these are all some of the defects when you see it. What I showed was schematic diagram. So, you can see here blowholes are there. These are all porosities which are there. Cold shut is there. So, this is hot tear. These are inclusions of sand which is coming there. this is mismatch and you can have short pore. To recap, what did we see in this particular lecture? We saw casting classifications, type of casting, sand casting, die casting, permanent mold, expandable mold, permanent pattern, expandable patterns. Then we saw various casting techniques, application of casting in different segments, defects in casting. Then we tabulated a comparison between various processes. Now, I will give you an exercise so that you can try doing this and see the importance of casting. And here you can try to produce the output in any of the casting methods. There is nothing called universal. I want to make a camera lens cover. Cover in the sense, there is a lens, there is a camera, there is a lens. So, there is a tube which comes in it. So, now I want to produce the camera, the tube, right, and the front end where I can press fit a lens. I hope I am clear. I have a camera, assuming that this is a camera. So, in the camera you have a tube which is like this, right, and then in the front part I would like to press fit a lens, so that I can use it like a camera. So, try to come out with a process, which process I will use in casting, such that I can produce the entire camera with the tube in one shot. This is first example. Second example is, I want to make lens. I want to make lens for a camera. Which casting process do I choose? The third question is, I want to manufacture a contact lens which is put in your eyes. Which casting process do you choose? So, I have given 3 examples. So, with these 3 examples, you should try to identify through books, do not go to Google, through books, through whatever I have taught, which one do I choose to make the product, whatever I have specified. We have used all these references for making these slides. Thank you very much.